Good afternoon, folks. I'm Eric Hagopian. My company is called Hoppe Technologies. Hoppe Technologies is located in booth 4088, and we are part of Team New England, which is a group of companies from New England exhibiting here with multiple different applications. And we're having a cocktail reception at 4 o'clock that we'd like to invite you to come to and have a Sam Adams on us. So that's your benefit for having spent your time here today. So just to give you a little sort of a brief description about the company before I get into the application that I'm talking about. Again, my name is Eric Hagopian. I'm the president of Hoppe Technologies, and we are talking today specifically about what we like to call IVD, or our Integrated Verification Department. And basically what IVD is it's in-cycle, on-machine inspection of product while it's being manufactured. So this is really a problem that has needed to be solved for many years. As we've gotten more, factories have become more automated, they need more inspection capabilities at off-hour time. So it's, again, the definition is a closed-loop system in which parts are being inspected in real time by the machine tool on which they're fabricated. On the left-hand side of the screen is an award, and in 2010, last year, the National Tooling and Machining Association, a member association of over 1,500 companies, we submitted our innovation, and we were awarded the 2010 Technology Award from the National Tooling and Machining Association out of all the submittals that were sent in. So we're very proud of that. So sort of a little bit on the company so that you can understand why we needed to do what we did. We're a 70-year-old company. We started in business in 1941. We employ about 90 people. Our annual revenues are in the $20 million range. Our primary business is aerospace and defense, but we do play a little bit in the medical arena, some semiconductor, optics, satellites, and so forth. So we're pretty broad in terms of our market. We specialize, though, in medium to higher complex parts, and assemblies, so that the commodity type items aren't items that we're normally interested in or really equipped for. We're very competitive in the medium to higher complexity arena, and we use almost exclusively fully automated CNC machines, palletized systems with as many as 36 pallets, and with each machine having as many as 352 tool pockets, possible tool combinations. Our average lot size is somewhere in the 50 to 250 piece range, although we routinely do development work, say 5 to 25 pieces, and we often, on our fully automated systems, we will do quantities of 10 and 20,000 pieces on an annual basis. So we're not in the automotive, large, huge quantity arena, but we're in that sort of medium to higher volume range. Again, our factory is fully automated. We run 24 hours, 7 days a week, 365 days a year, again, through the advent of the automation. We're AS9100 certified and ISO 9000 certified. We're also certified by the Federal Aviation Administration for overhaul and repair work in our factory for aircraft. So sort of a description of some of the machines that we have. You see the large photo on the left is a line view of one of our Palletech systems. We use Mazak equipment, not exclusively, but primarily. And this is a picture of a 30 pallet robotic linear line feeding 3 horizontal 500 millimeter horizontal machining centers that again run on a lights out basis. We also have 2 other lines, 5-axis lines. We do continuous path 5-axis machining on a 24-hour, 7-day-a-week basis. And we've got some incredible samples of some of the work that we do over at our booth. So when you come over to have a beer, we'd be happy to talk to you about it. In addition to milling, we have a series of 8 multitasking machines. These multitasking machines make parts that would fit in your hand, whether they're very small or say up to 4.5 or 5 inches in diameter in that shape. These machines are doing turning and milling integrated into one machine. So it really is a done-in-one application that allows us to run, again, lights out on a bar-fed or robotically fed application. We have 2-axis robot pick-and-place systems as well. So from a quality assurance perspective, final acceptance on all products goes through our quality assurance department, and there we use the latest technology in Zeiss CMMs, but you can only check the parts after they're done in the quality department. And so, the throughput is relatively small in the quality department, whereas the throughput in the manufacturing department is rather large. So there comes the problem. The problem is, with all this wonderful equipment, we found ourselves with too much. We had too much of a good thing. We had so much lights out capacity, and we're producing so many parts that we overwhelmed our quality department. We don't have a QA function. We don't have people fully staffed in our quality assurance department on Christmas and New Year's and at 3 o'clock in the morning and swing shifts and so forth. So we're producing lots and lots of parts without having the ability to have somebody overseeing the operation. The other thing, of course, is that when the man shift comes in, they have too many parts to go through, and it's too late at that point to check the parts because they're already made. So the cost of poor quality is something that we really found ourselves paying attention to. The solution was to come up with a way to get the machines to do their own inspection. And so, what we did was we came up with a lights out inspection capability that increases our manufacturing throughput, and it helps us to understand what our productivity and the statistical capability of our processes are, and it provides a reporting mechanism for us to go back to our customers and talk to them about the process capability that we have on their parts. It gives them a very high level, high degree of satisfaction that their parts are being produced on an automated basis, and good parts are going to wind up at their factory, and we're going to have no escapes. If you have a good process, you're going to make good parts. Make good parts, they're not going to come back, and that's what we're looking for. So that's kind of the background of the company and the background of why we did what we did. So initially what we looked at was we looked at the products that are out on the market today, and one of the products is a system called PC Demus NC. And so those of you who are familiar with CMM software, you know that PC Demus is a language for programming for CMMs. The NC portion obviously is the numerical control piece that marries a CMM program with your CNC program and allows you to inspect on the machine. The limitation of the software and the limitation of the machine tool, however, made it such that you can only inspect on center line of the spindle. And when you're talking about 8-axis, 5-axis machine tools, you need to be able to check in all these different axes. We manufacture complex fuel control housings. You'll see a small video here in a second. And we need to be able to get inside of those passageways and so forth. So, that was the impetus behind trying to come up with something that hadn't been come up with before, or hadn't been invented before, because we couldn't find a commercial solution to our problem. So the components of IVD are not just the manufacturing system or the machine tool, not just the software that does the actual inspection, and not the sort of patch that we wrote to marry it all together, but there's a lot more parts, okay? So this diagram shows the tool magazine and one of our machine tools with some of the components of IVD. So you see a chip fan, and a chip fan is basically The tool that is at the top of that list, it's sort of purple, and when it spins up to 10 to 12,000 RPM, the fan blades open with centrifugal force, and it provides a tremendous amount of air to blow off the chips and coolant, because of course, again, you're inspecting in a manufacturing environment. We use two different kinds of probes depending on the accuracy and repeatability that we need. So the OMP 400 strain probe is an extremely highly accurate probe, and we combine that with the OMP 60 kinematic probe, which is a more robust but a little less on the accuracy side. It depends on what you're checking as to what your what probes that you require. So the way that it works is step one is you inspect the machine tool inspects the parts using the applicable probes. And again, the machine tools generally come with one probe from the factory. We have set up our machines to have as many as 5 unique touch probes, so that we can have a star probe, a long probe, a short probe, just like a CMM with a tool changer. Because our machines are equipped with high capacity tool changers, it allows us to be able to utilize that tool changer to have as many tools as we need. Now, each one of the touch probes heads is about $8 grand, so it's not like you're going to go out and put 20 of these things on the machine just for the hell of it. You're going to really utilize what you need. Step two is that our programmer creates an inspection, or our programmer creates a program. That program inspects the parts, and it creates an inspection report from that raw data that the machine provides. And then step three is that custom software piece that we develop sends that inspection report right out to the load and unload station, so that when the operator finishes, when the machine finishes manufacturing a particular item, and that pallet is delivered to the unload station, the operator sees in real time an actual inspection report right in front of him or her that allows them to be able to tell whether that product is a good product before they remove it from the pallet or the fixture or whatever the case may be. At the same time, we store all that data on our network so that we're able to retrieve inspection reports on the product. If it's the next day, for example, and it ran on the night shift before, we want to look at those inspection reports, we can retrieve that data. This is what an example of what one of those inspection reports looks like. So what you see is you've got a three-dimensional rendering of the part with lines to the critical characteristics that we're checking. And so basically, we got the labels. They feature on identifying the features on the CAD label. These green tolerance bars visually show the deviation from nominal. Again, we're doing typical statistical process control where we take the tolerance, divide it in half, and that's our manufacturing tolerance. And then, of course, we have all the information, the feature name, the nominal size, the measured size, and then the deviation from nominal. Those things are reported on the computer screen at the point where the operator takes the finished material off. Down in the bottom right-hand corner, you see a true position measurement, which again is something that you couldn't get at a plate check, for example, on the side of the machine. You have to bring it to your quality department and get in line. SPC, when you're running lights out, you got to have a process capability, that's capable, and so you have to have process capability studies, and in order to get the process capability study, you have to have data. Well, we've got loads of data, and we've got data coming through on an automated basis, which allows us to be able to populate statistical process control charts in real time, and before there's a deviation from nominal, we can see that trend as we're going. By the way, the fellow that's pictured on the right here is 24 years old. He's a recent college graduate from Wentworth Institute of Technology in Boston, and he's the one who solved this problem. So it wasn't some guy with snow on the mountain. It was a kid, a really smart kid. And I would encourage anybody who's looking to develop new technology to tap into the energy and the minds of young folks that are, in many ways, smarter than their elders. So the machines, this is a picture of essentially what our little patch software looks like. And so basically what we've got is we've got a bunch of variables that we were able to select. So you select the machine, the number of tools that you want to use, what that particular tool type is. This heavy tool, yes or no, is something that, again, we've through process of failures and successes, we found that we needed to tell the machine whether we had a big tool in the spindle or a little tool in the spindle for tool change properties. So, for example, if you put a Renishaw strain probe in the spindle and you tool change it fast, you'll wind up with accuracy problems. So, we really had to sort of figure it out as we went. We show the nominal size, and then this update percent. Basically what that means is that we take the tolerance and we say, well, what percentage of the tolerance do we want to use before we tell the machine tool that we want it to automatically update the offset? Now that's something that I didn't say yet, but that's what we're doing. The machine has its own intelligence, and it knows based on the information that it's gathering, how far away from nominal it is, and it can automatically change itself, change the offset to bring that feature back into tolerance or back closer into closer to the nominal. So what we do is we give it a variable. We say in this case it was 30%. We want to, if it exceeds 30% from nominal, then we'll go ahead and change it. If it's greater than 2 thousandths in this case, we're just going to ignore that piece of data. So the advantages are you get parts with, you can trace with serial numbers. You can inspect and inspect right to a serial number. The machine can be set to alarm out if the features are out of tolerance. The probes can be used automatically to find the work coordinates. Is a number of different things that advantages here. So just show you a quick video. Take 20 seconds. This is what it looks like on a 5-axis machine. This is a complex fuel control for an aircraft engine, and it's being checked in real time in full 5-axis. So that again, you can't check everything with one probe, so you have to have multiple probes. And the idea is that you check the shallow stuff with the small probe, and then it'll tool change into a larger probe. This is being done on a Mazak Variaxis 630, which is an 18,000 RPM spindle machine with coolant-fed tools and all that other good stuff. Okay. Let's see. So are there any questions? Yes, sir. Okay, so the question is, do we have dedicated programmers for this application? The answer is yes. We have one dedicated programmer for IVD, and we also use Vericut. So the Vericut programmer and the inspection programmer sit next to each other, and we integrate the inspection program to the CNC program using Vericut. Anybody else? Sir? Yeah, question is, can you measure parts while they're being cut? And the answer is no. It has to be in a static, machine static situation. Okay, since there's no other questions, I want to thank everybody and again welcome you to come to our booth 4088 for free Sam Adams. Thank you very much for your attention.